All right, so we're going to talk for a minute about the chemistry of biology, and I'm hoping that this is not too daunting of a subject for everyone. It's going to take a couple of lectures for me to get through it. I highly recommend carefully reading your book, checking out online resources if you aren't quite understanding the way I'm phrasing things. So let's jump in. We can start by taking a peek at our learning outcomes. So distinguish between atoms and elements, illustrate the structure of an atom, define an isotope and summarize its application in both medicine and biology, and distinguish between ionic and covalent bonds. We're going to get to as many of those as we can. So let's jump in. So we have certain subatomic particles that make up atoms, as their name implies. And we have these ideas of atomic number, mass number, atomic weight, isotopes, Bohr diagrams, valence electrons, and these are just some extra things we're going to be talking about. So this is a diagram. It's a very cheesy diagram I drew in PowerPoint of an atom. And these blue things here are protons. These yellow things are neutrons, and these red things, or that one red thing, is an electron. So protons and neutrons together make up the nucleus of an atom, and obviously nuclei in an atom are going to be a bit different than the nuclei of a cell. So protons and neutrons have the same mass, one atomic mass unit, which is equal to 1.66 times 10 to the negative 27 kilograms. I don't want you to know that number. I just want you to see it to kind of put it in perspective how tiny these things are. So as you can see here, this sort of just summarizes all the information I just said in the table. So protons have 1 AMU, have a positive charge. Neutrons have 1 AMU and have no net charge. And electrons are 0 AMU. They weigh something, which is why it's approximately 0, but they don't weigh a lot. And they have a negative charge. What makes an atom unique? Well, what makes an atom unique is the number of protons that it has. So you can see like helium, represented by an H here, has 1 proton. I'm sorry, hydrogen has 1 proton. Helium has 2. Lithium has 3. Beryllium has 4 protons. And so on, right up the list. And the number of protons is represented here by the atomic number. So the atomic number of hydrogen is 1 because hydrogen has 1 proton. So the atomic number, like I just said, is how many protons, and the atomic mass is the average mass number of the different types of that element. And I'm going to explain a little bit more about that later on. So what is the atomic number of an atom with 79 protons? Well, that's a pretty easy question, I think, because the atomic number is the same as the number of protons. So you go down to 79 here, 79 protons, the atomic number of gold is 79. So atomic number is the same as the number of protons. Oh, there's an arrow for it right there. And there you have it, 79, gold. So the atomic number is how many protons an atom has. The mass number is the average mass. The atomic mass is the average mass number of different isotopes of the atoms. So if you add up the number of neutrons, you add up the number of protons, this will tell you how many AMUs your atom weighs, and it will give you a mass number. So if I had 10 neutrons and 9 protons, my mass number of that atom would be 19. What kind of atom is this? How can you tell? So it has 9 protons. That's how you can tell. So which element has 9 protons? Well, that is this fluoride atom here. It has 9 protons. Its atomic number is 9. So this is the one. And you might say, well, what if it had 8 protons? What if a fluoride had 8 protons? Well, it wouldn't be a fluoride anymore. It would then be an oxygen. Okay. What makes an atom, what makes an element unique is the number of protons that it has. and there's an arrow pointing to the F. And I'm just kind of beating a dead horse at this point, but yes, F, 9 protons, atomic mass, or not atomic mass, but the atomic number 9 protons. So you'll notice that the atomic mass listed here is 18.9984. And typically protons, typically the number of protons in an atom is equal to the number of neutrons. So you might be saying to yourself, or probably saying to me, how is it possible that you're taking two things whose atomic mass are 1, and for one thing, you're getting a number other than 18, because if you had 9 protons, you would expect there to be also 9 neutrons, and you're getting this weird, like, decimal point business. How is that even possible? Exactly what I said. So the reason for this is that there are different forms of the fluorine atom. I've been saying fluoride, I meant fluorine. There's different ways that this fluorine atom can exist. Both of these have 9 protons, but this one here has an extra neutron. So its atomic mass is 19, and this one's atomic mass is 18, because it has 1 less neutron. These are what are referred to as isotopes. So like I just said, this one has an extra neutron. This one has 1 less neutron. So atoms with the same number of protons but different number of neutrons are called isotopes. So this one, again, 1 extra neutron. When you average the mass number of every isotope of fluorine, you wind up with that atomic mass if you factor in the relative abundance. I'm going to talk about that in a second. But this is how you wind up with an atomic mass of 18.9984, even though protons and neutrons all sort of weigh 1. That's an average. So let's do a quick example. I don't anticipate that you're going to be able to do anything like this. I just kind of want to show you how it works. Okay. So if we were going to empirically calculate the mass of carbon, and we have this carbon-12 isotope, 6 protons, 6 neutrons. We have this carbon-13 isotope, 6 protons, 7 neutrons. And you can see over here that most of them, 98% of them, are this carbon-12 in this sample that you've got. So like I just said, each one has 6 protons because they're carbon. If they had 7, they'd be something else. If they had 5, they'd be something else. They have 6 because they are carbon. Let's figure out what the mass number is. So the mass number is, again, adding up the number of protons and the number of neutrons together. That is math you should be able to do, by the way. So let's say in our sample, you multiply this 12 by this 2%, so you're weighting against its relative abundance. You multiply this 13 by 98%, you get 0.26. You add them together, and you get 12.02 atomic mass units. All right. If you didn't follow that perfectly, don't worry about it super much. It's just I'm showing you why it is that your atomic mass numbers on your periodic table aren't just adding up to an even round number. So the thing about isotopes is some of them are radioactive and they tend to decay. And so because they decay, we can use them in medicine to figure out what's wrong with you potentially. So you put someone through a PET scan or a positron emission tomography scan, and you have them drink some iodine 131. Iodine is a very slightly radioactive substance, and iodine accumulates in your thyroid. So therefore, so will this radioactive version of iodine. So I just wanted to ask really quick, how many neutrons does iodine 131 have? So you know how many protons it has, 53, right? It's atomic number. So how many neutrons does it have if its total atomic mass is 131? You should be able to calculate that. The way you calculate that is you just take 131 and you subtract 53, and that will tell you the number of neutrons. So here's a picture of, this is sort of diagrammatic, like cartoony thing of a thyroid gland here. And you can see on the left here is a PET scan of a thyroid of someone that has taken a drink of some radioactive iodine. And as you can see, part of it is very well illuminated, and part of it is apparently not visible to this PET scan. So there's a problem with this segment of the thyroid over here. Okay, that's the basic way that we're using these things in medicine. You're drinking some iodine, and you're, oh, you know, look, it's showing up here, but somehow, for some reason, it's not showing up there. So there's your problem. So moving on, we have various ways that we could model and understand how atoms work. And so this guy, Niels Bohr, created this way of modeling how an atom works. And he thought of it kind of like a little solar system onto itself, where you have this nucleus, which is kind of like the sun, and then you have electrons orbiting it. Turns out he wasn't super right. But it's a really fantastic way of conceptualizing, thinking about, and understanding how atoms work. So let's talk about the Bohr model. A neutral atom has an equal number of protons and electrons. So if you look here, you see that the atomic number is 17 for chlorine. If you assume that it is a neutral atom of chlorine, how many electrons does it? It has 17 electrons because it's neutral, and the number of protons is balanced out by the number of electrons. So if we were to take our nucleus and shrink it down to a little dot, you'll find that the electrons, at least in the Bohr model, exist in shells around the nucleus. So the first shell around the nucleus can hold 2 electrons. We'll put those there. There's these red things, remember, are electrons. And then the shell beyond that can hold 8. So again, the first shell can hold 2, and the next shells can hold 8. Keep in mind, we are creating a Bohr model of chlorine. So how many electrons are represented here, and how many more are left to go? So we've got, get back to the pointer here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. Chlorine's atomic number is 17, and we're modeling a neutral atom of chlorine, so we have 7 more to go. Let's add those in. So we've got 11, 12, 13, 14, 15, 16, and 17. So this is what chlorine looks like under the Bohr model. The valence shell, or the outermost shell, are the most important for chemical reactions. These are the furthest out, and so these are going to be the only ones that can really react with anything. Also, because of a little concept called the octet rule, they're going to be the most reactive by far. The octet rule is basically just that atoms want to have a full shell of electrons. So you can use the groups here to figure out how many valence electrons each of these things have, which I think is one of the very cool features of the periodic table. So here it falls apart with helium, but don't worry about that. So helium, lithium, sodium, potassium all have 1 valence electron in their outermost shell. Beryllium, magnesium, calcium, strontium, etc. have 2 valence electrons in their outermost shell. And then we skip over these transitional metals. And we get over here to find these elements have 3, these elements have 4, these elements have 5, these elements have 6, these elements have 7, and these elements have 8 valence shells in their outermost, valence electrons in their outermost shell. So, like I said, elements typically want to have their outermost shell filled. And I'm saying want again, they don't really want anything. It's just a property that we've discovered in nature that an outermost shell that's filled is more stable. So these ones have 8 in their outermost shell. And you'll remember from a few slides ago that the innermost valence shell can hold 2 electrons and the subsequent shells can hold 8 electrons. And so you'll notice these are what is referred to, or what are referred to as the noble gases. These do not react. These are just happy, fairly stable gases that won't react because they have a filled valence shell. So now we're going to think about chlorine in another way, which is the electron dot structure. So how many valence electrons does chlorine have? Chlorine's number 17 over here. So remember, you can determine how many electrons an element has in its valence shell by counting the group number that it's in. So according to this method, chlorine has 7 electrons in its valence shell. Okay, so these elements have 1, these elements have 2, these elements have 3, 4, 5, 6, 7. There's chlorine right there. So chlorine has 7 electrons in its valence shell. So, and like I said, electrons like to pair with one another so they can try to fulfill that octet rule. And chlorine has 7. And we are left with this lone unpaired electron, which is a rather unstable configuration. Cl- does not happen often in nature because it's, like I said, it's quite unstable. So atoms that, like I said, want to have filled shells of electrons. And so chlorine can either lose that electron, or I mean, it can lose 7 electrons, which is a pretty mean feat. That's pretty difficult to happen, or it can just gain 1 more. So in order to get its electron, I don't know what that is, electron, in order to get another electron and fill its outermost shell, chlorine pairs with another atom that has a spare electron. So where are the atoms that have 1 spare valence electron? So remember, you can figure out how many valence electrons something has by just counting which group it is. So 1, easy. These all have 1 valence electron. So any of these elements here will easily pair with chlorine so that it can have a filled shell. Those guys right there. So I picked sodium because sodium chloride is something that we're all very, very familiar with, table salt. So here's the Lewis dot structure, as it's called, of sodium. It has 1 valence electron, remember? 1 valence electron, there it is. Dot structures, we're only drawing the 1. Chlorine has 7 out here. And if these 2 elements get together, they can form sodium chloride, and they can each have something like a filled outer valence shell, or in this case, an empty outer valence shell. And what happens there is because chlorine is more what's called electronegative, it sort of hogs that electron away, and it gains a negative charge. Sodium, on the other hand, just lost its electron, and so it gains a slightly positive charge, and this is what's referred to as an ionic bond.